Hi guys, and welcome back to my channel. Today I am very pleased and excited to introduce you the basic mathematics for you if you want to become an actuarial student. Some of you may know it already because it's like high school mathematics, but it is a basic for you if you want to become an actuarial student. My university is going to open soon, and I'm gonna be in an actual lesson to become an actuary. So I'm very excited for this preparation. I'm going to prepare myself as well. I mean, along with you, I'm going to reveal it and prepare myself for the next lesson. So I hope you enjoy it. Okay, as you may know, in this video I'm going to talk about general probability, which include basic probability concepts and conditional probability, and some of new things that you might not have heard about is independent events and Bayes' theorem, counting techniques, permutation and combinations. So I think this will lead to distributions and risk management in your future lessons. So let's get started. Before we go any further, I'm going to introduce you this practical issue for actuaries that actuaries face in their careers. So these are some problems. It says like is n large enough to say that f divided by n has become a good approximation to the probability of the event of interest. So data collection costs money, right? And decision must be made. So the sample that should be large enough, but not larger than necessary to give the precisions. So if you wanted to become an actuary, these are some issues that you may face in the future, but it's kind of be fun issues. So you can do it, and I think you can find all the solutions and make the right decision in the future if you have enough knowledge. And yes, anything is possible. Don't be discouraged. So we are going to random experiments, and I think you have already know sample span, events, and all the sets which is like a complement, union, and intersections. So I'm not going to talk much about this. The last thing is law of addition, which is kind of be necessary thing that you have to remember or you have to understand it. So for example, the probability of A union B equal to the probability of A plus the probability of B minus probability of A intersection B is kind of be memorable formula for us to like in the probability lessons. So I think you have already understand it. So there is some exclusive events here, like when probability of A intersection B equal to 0, then the probability of A union B equal to the probability of A plus B, because A and B do not overlap. So I'm moving to conditional probability here. The conditional probability is the probability of event A given that event B has occurred. So it can be written like this: A, the probability of A given B. And the formula of this is the probability of A given B equal to the probability of A intersection B divided by the probability of B for the probability of B greater than 0. So let's look at the example here to illustrate and for you to have more understanding about conditional probability. It's kind of be a bit complex and news to you, but I think you can do it. So let's say you roll a dice from right hand and you roll a dice from left hand. Let A equal to roll a die from left hand greater than rolling a die from right hand, and let B be you get number 4 from rolling a die on left hand. So I want you to find the probability of A given B and the probability of B given A, and also the probability of A and B. So we are going to find the probability of A, which is rolling a die from left hand greater than right hand. So it is 15 over 36, and it can be cancelled out to 5 over 12. And the probability of B, of course, 6 events, so it will be 6 over 36, and it can be cancelled out to 1 over 6. So the probability of A given B is going to be the probability of A intersection B divided by the probability of B. So we already have the probability of B. So let's say the probability of A intersection B. So you need to have like left hand die greater than right hand die, and it is number 4 on left hand. So you have 3 events, which is 4, 1, 4, 2, and 4, 3. The answer would be 3 over 6. Then you have to find the probability of B given A, and it is 3 over 15. And let's look at the 2 events that A and B are independent, so it not affect to each other. And I will give you 3 checklists here. For give you an example, let's say we roll a dice again, and let A be the event outcomes and B be the outcome that's less than 4. So instead A we will have 2, 4, 6, and instead B we will have 1, 2, 3. Is it independent? We will see. Your question is probability of A intersection B equal to the probability of A times the probability of B. We are going to find the probability of A intersection B, which is the outcomes are even and less than 4. So we have one possible outcome, which is 2. 2 is an even outcomes and less than 4. So it's 1 over 6. The probability of A is 3 over 6, and the probability of B is also 3 over 6. So 3 over 6 times 3 over 6 is not equal to 1 over 6. So it is not an independent event. This is the fun part that I discovered, because so far it's kind of be boring because it's all mathematics, and this is more practical for you. Suppose 2 websites has 2 independent file servers, and each server has 99% reliability. And what is the total system reliabilities? So let's give F1 be the event that server 1 is false, and let F2 be the event that server 2 is false. And you will have the probability of F1 equal 1 minus 0.99, and you will get 0.01. Similarly, you will have the probability of F2 equal to 1 minus 0.99. What about the probability of F1 intersection F2? It is equal to probability of F1 times probability of F2, which is 0.0001. So to sum up, the probabilities that at least one server is up is 1 minus 0.0001, which is 0.9999. But dual file servers improve 99.99% reliabilities. I was like, oh my god, math is getting fun. So I hope you enjoy it like me. And we are going to move on to the redundancy. I've never heard about this before, but I kept read over it, and I see this interesting example. It says NASA's space shuttle has 3 flight computers. Its function are independent, and each computer has 0.03 chance of failure. So let F be event that computer fail. So let's find the probability of all 3 fail. It will be the probability of F1 intersection F2 and intersection F3. So you will have 0.03 times 0.03 and times 0.03. So what does this mean? It means the probability of all 3 computers failed is 27 in 1 million missions. How interesting is that? So it comes to this question, how much redundancy is needed? So we are going to suppose web server is up, the percentage of web server is up is 94%, and the percentage of the server is down is 0.06. How many servers are needed to ensure the system is up at least 99.99% of the time? So we are going to find the probability when the server down. So it will be 1 minus 0.9999, and you will get 0.0001. Then we are looking to if we use 2 servers. If we use 2 servers, then it will be 0.0036. So it is not quite close to 0.0001 enough. So I think we need more servers. So let's calculate 3 servers, and you will get 0.000216. And that is not enough. We need 4 servers. And the result that we get is 0.0001,296. And that is very close to So I guess we have enough example now, and we are going to move on to the different subject called law of total probability. So we are going to find the probability of winning. And given that playing at home, the probability of playing at home is 0.6 and playing away is 0.4. So the probability of winning is equal to the probability of winning at home union to the probability of winning away, right? And it will be equal to the probability of W intersection H plus the probability of W intersection H complement Again, the property of W intersection H, which is the property of H times the property of W given H, and similarly to the winning away. And the property of winning will be 0.63. I'm sorry if it is getting too complicated. Let's do it in terms of A and B. If A and B, the property of B equal to the property of A times the property of B given A plus the property of A complements times the property of the probability of B given A complement. So in this Bayes rule or Bayes theorem, we are going to use the same event, but this time we are going to find the probability of playing at home and winning. We will use the formula, so it will be the probability of playing at home and win divided by the probability of winning. The probability of playing at home and winning can be written as the probability of playing at home times the probability of winning given that playing at home divided by the probability of winning, which we already done that before. So it will get 0.7143. So let's look at this. There are different areas, many different areas. Set B is cover or area. So if we want to find the probability of AK given B, it will be probability of AK times probability of B given AK divided by the probability of A1 times the probability of B given A1, and we do like this until AN. Now I am going to bring you till the last lesson for today is fundamental rule of counting. Let's say if even A can occur in N1 ways and even B can occur in N2 ways, then the even A and B can occur in N1 times N2 ways. So factorial is very essential for this lesson. You need to know the concept of factorial. Like n factorial is equal to n times n minus 1 and minus 2 times to the 1. For example, 5 factorials is equal to 120. We will use factorials when choosing items like the service task must take 3 stops with each A, B, C. In how many ways could the 3 stops can be arranged? So it will be 3 factorials, which is equal to 6. Then you will need to know the concept of permutations. We use permutation when choose R items at random without replacement from a group of n items. So it can be written as NPR equal to n factorial divided by n minus r factorial. For example, how many possible arrangements there are when we select R items? Yes, so we will use permutation in this case. Apart from permutation, there are combinations. We will use combinations as a collection of R items chosen random without replacement from n items. Order is not important in this case, so it can be written as NCR equal to n factorial divided by r factorial times n minus r factorial. So in this case, order is not important. Only thing that matters is which R items are chosen regardless of how they are arranged. I will give you some note here for you to practice more exercise and more questions for you to review what you have learned today. Okay guys, that is for today's lessons. I hope you enjoyed the video all along, and if you are a beginner like me, I hope you can follow along with me. There will be much more lessons in this actual journey, so I promise to help you through the journey. I'm going to help myself as well because it is going to be tough time and fun times as well. I hope you fall in love with the process of learning and having passion on what you learn, and you'll be happy. Thank you for today. See you.